morning, dear student. In last video we had discussed about pulley. In that I had explained single fixed pulley and a single movable pulley. Today we shall begin with the combination of pulleys. So there are two kind of combinations for pulleys. Okay, one is a combination in which there are number of movable pulleys and a single fixed pulley. This is the first system in which there are number of movable pulleys and a single fixed pulley. And the second one is there are two blocks and there are number of pulleys in each block. Okay, and the first block is supported to the upper block is supported by a rigid support. The second one is movable over the first block with the help of a tackle. This system is known as block and tackle system. So we will begin with the first one, where we are using one fixed pulley and other movable pulleys. So I have drawn a diagram here. As you can see here, this is a rigid support and this is pulley number D, which is a single fixed pulley, and A, B, C, these are three movable pulleys. All are being supported by a strong tackle or string. Here we are applying the effort on the tackle here, E. That is, in the effort, E is the effort in the downward direction, and the load is being suspended by the A pulley. The load is on the A pulley. Is it clear? So this system is required when we want a very high mechanical advantage. As you all know, mechanical advantage of a single fixed pulley is only one. It is used for changing the direction, and the mechanical advantage of a single movable pulley is 2. But if we want mechanical advantage greater than 2, then we have to use number of pulleys in a system. Okay, if we have to lift a very heavy load, we need number of pulleys in a system. So we are using this system which is a combination number of movable pulleys and a single fixed pulley. So now we will calculate the mechanical advantage of this system. Now we will find out the mechanical advantage of this combination of the pulleys. Okay, so first of all we talk about the load. The load is being handed to the pulley A. Okay, so L is the load that is acting in the downward direction. Now this load is being supported by two tensions T1. So L is equal to twice T1. L is equal to load is equal to twice T1. Okay. Now this tension T1, this string is being attached to the pulley number B, which is another movable pulley. So all this load T1 is supported by T2. T1 is acting. T2 is equal to T1. So twice T2 is equal to T1, and then this twice T3 is equal to T2. You should remember this. Whatever load is hanging here, L is equal to twice T1, then twice T2 is equal to T1, then twice T3 is equal to T2, and effort is equal to T3. So we are writing here mechanical advantage, effort is equal to T3. Load is equal to twice T1. So we get the value T1 is equal to L by 2. At the pulley B, twice T2. Tension in the upward direction T2. They are balancing the tension T1. So T2 is equal to T1 upon 2, which is equal to L upon 2 raised to power 2. At the pulley C, T3, which is acting in the upward towards the rigid end, 2T3 is equal to T2. We substitute the value of T3 is equal to T2 by 2. Substitute the value of T2. We get L upon 2 raised to power 3. Now we know that E is equal to T3. So instead of T3 we write E. E is equal to L upon 2 raised to power 3. Mechanical advantage is equal to load upon effort. So mechanical advantage is equal to 2 raised to power 3. Now if we look at the result, mechanical advantage of this combination of pulleys is 2 raised to power 3. What is the index? This is equal to the number of movable pulleys in the system. There are 3 movable pulleys that are used in this system. So mechanical advantage is 2 raised to power 3, which is equal to 8. Now suppose if there are n movable pulleys that are used in this system, in that case the mechanical advantage of the whole combination of pulleys will be equal to 2 raised to power n. What about the single fixed pulley? The single fixed pulley has mechanical advantage of equivalent to 1. So it is only used to change the direction. Is it clear? So we have mechanical advantage of the whole combination depends upon only the number of movable pulleys. Now we will calculate velocity ratio. As you all know, velocity ratio is the distance moved by the effort to the distance moved by the load. So distance moved by the effort to the distance moved by the load. So as one end of the each string passing over a movable pulley is fixed. Okay, one end this is fixed, the other end is fixed to the second movable pulley. So the other end of the string moves up twice the distance moved with the axle of the movable pulley. If the load L is moved up by a distance x, the other end will move by a distance 2x. Is it clear? If the distance moved by the load is x, the other end will move by a distance 2x. So the pulley B will move by a distance 2x. This is moved by x, pulley B will move by 2x, and then twice of this will be moving. So pulley C will be pulled by 2 into 2x, 4x, and pulley D twice of this, 2 into 2 into 2, 2 raised to power 3 times the distance. So pulley D will be pulled by a distance of 2 raised to power 3x. Is it clear? So x, whatever is the distance moved by the load, twice B pulley will be pulled up, and twice of whatever B is being pulled, C will be pulled up, and twice of that D will be pulled up. So effort will be 2 raised to power 3 times the distance moved by the load. So distance moved by the load is x. This is equal to 2 raised to power 3x upon x. So velocity ratio is equal to 2 raised to power 3. Now again here mechanical advantage and velocity ratio for the ideal condition is the same, that is equal to 2 raised to power 3. That is equal to number of pulleys that we are using, movable pulleys that we are using in this combination. Yeah. Now next we talk about the efficiency. Now efficiency is mechanical advantage upon velocity ratio. So mechanical advantage of this combination is 2 raised to power 3. We write efficiency, mechanical advantage upon velocity ratio. This is 2 raised to power 3 upon 2 raised to power 3 equal to 1 or 100%. So efficiency of this combination is again 100%. This is for ideal condition. The next combination of pulley is block and tackle system. So as the name suggests, there are blocks. There are 2 blocks. One that is supported to the rigid end. The other one that is supported by the tackle and is a movable block. Each block, what is a block? Block is a frame in which there are number of pulleys. So there is one block which has got 3 pulleys in it. Okay, and this is supported by a rigid support. And we have another block that is movable and is fixed to the upper block with the help of a tackle. It is hanging on the tackle. Okay, so this is movable block that will move up and down. Okay, now this system is a block and tackle system. Generally, when we talk about a block and tackle system, there are 3 pulleys or more than, there are 3 pulleys or more than 3 pulleys in the upper and the lower block. Okay, that will depend upon the mechanical advantage that we want to take from the block and tackle system. But there are two kinds of block and tackle system. One which have got equal number of police both in the fixed block and the movable block. The second one is a system in which the number of police in the movable block is less than the number of police in the fixed block. That is, in the lower movable block, like you can see here, there are number 1, 2 and 3. 3 police in the upper block, that is a fixed block, and there are only 2 police in the lower block. Now what is most important here is to put the tackle. You are asked to draw the tackle in the board examination. This question is more often asked in the examination. So you are supposed to put the tackle. So when we have a block and tackle system in which the number of police are unequal in the upper block and the lower block, then we start putting the tackle from the lower end. See, now you can see how I put the tackle. I have started putting the tackle in this end. It moves here and then it goes down here, then it goes to the upper pulley, then it goes to the lower pulley in the lower block, and then to the topmost pulley and then down. So you are supposed to put the tackle in the tackle, which is a string around the pulleys. So when we are having a block and tackle system in which the number of pulleys in the upper block and lower block are unequal, then we start from the lower block and we get the effort in the downward direction. Is it clear? Now there is only one string. There is only one string that is wound around all the pulleys. So the tension in all the segments of the string will be equal. Is it clear? Tension in all the segments. So there are a number of segments. We start putting tensions here. The first segment, tension T. Here again tension T. And here again tension T. Okay. Then this tension T and downward direction F1. This is in the downward direction. There is an F1, and the last one is tension. So this is an open end. Now we have to find out the mechanical advantage of this single fix this block and tackle system. So we have mechanical advantage. Effort equal to tension T. And how many tensions are supporting the load? There are 5 tensions. 1, 2, 3, 4 and 5. This tension is equivalent to effort. Now 5 segments, 1, 2, 3, 4 and 5. So load is equal to 5T. Okay. So mechanical advantage is equal to load upon effort, that is equal to 5T upon T, cancelled out, equal to 5. Okay. So mechanical advantage of this block and tackle system is equal to 5. Clear? Is it clear? Okay. Then we have velocity ratio. So velocity ratio of this system is distance of effort or upon distance of load. Now suppose there are n pulleys in the system. There are n pulleys in the system. Then the displacement of effort will be equal to ND and displacement of load will be equal to, here in this case there are 5, so 5D upon D is equal to 5 and efficiency equal to mechanical advantage upon velocity ratio equal to 5 upon 5 equal to 100% or equal to 1 or 1. That is the case for an ideal pulley. This This is the case for ideal pulley. Next we have a block and tackle system in which there are equal number of pulleys in both the blocks. So here I have drawn a block and tackle system in which there are 2 pulleys in the upper block and 2 pulleys in the lower block. The upper block is a fixed block and the lower block is movable block. Now again I will tell you how to put the tackle in this block and tackle system. So here we will start putting the tackle from the top hook here, and this will go, tackle will go like this from this end in the upward direction. We'll say come down and will go in the. So please learn to put the tackle, because you are asked to put the tackle in the block and tackle system in the examination. Okay. Now we have the load that is being hanged to the movable pulley, lower pulley L here. Now effort, the pulley is being pulled here from this open hand. This is effort here, so tension here. Each segment will have same amount of tension because this is only one piece of string. So now we put the tensions here, T, and T. Okay. So now we find out the mechanical advantage again of this system. Mechanical advantage is equal to load upon effort. Effort is equal to tension 1T here. This effort is equal to this tension. Now load is supported by how many tensions? Load is equal to 4T. 1, 2, 3 and 4. These are 4 segments of the string that are supporting the load. So L is equal to 4T. So mechanical advantage is equal to 4T upon T. That is equal to 4. Okay. Now if we generalize this, then what we have seen is when there were 5 pulleys, load was supported by 5 segments, so 5T. When we have 4 pulleys, load is supported by 4 tensions, so 4T. If there are n pulleys, then E will always be equal to single tension and N will be equal to NT. Okay, so mechanical advantage for n number of pulleys will be equal to NT upon T, that is equal to N. And velocity ratio, displacement of effort upon displacement of load will be equal to ND upon D equal to N. And efficiency will be equal to 100%. Is it clear? But all this is for an ideal condition. This is for ideal pulleys where there is no friction. The weight of the pulley is 0. Okay, there is no friction. The tackle is not extensible. So in the ideal condition only we have the system giving you 100% efficiency. Now in the practical conditions, we know that the pulleys are having certain amount of mass, so they are having weight. Okay, so all the pulleys, let us consider all these pulleys, they have a certain amount of weight. Okay, but the weight of the upper fixed block is supported by the rigid support, so it is not acting on the load. Is it clear? But the lower block is completely hanging over the tackle. So when we are lifting the load, we are also lifting the weight of the lower block, isn't it? So that will affect the efficiency of the machine and also the mechanical advantage of this block and tackle system. So let us consider that the load of the lower block is equal to W. Okay, we have taken the this lower movable blocks weight equivalent to W. Okay, and the weight that is hanging, the load that is hanging is L. Now we will find out the mechanical advantage of this pulley system. So total load here is L plus W. Now it is supported by, suppose there are n number of police in the system, so it is equal to nt. Now, n number of police in the lower block, so it is equal to nt. Okay, number of police in the lower block is n, so it is equal to nt. So n is equal to nt minus w. Okay, so n is the number of police, so nt l plus w equal to nt. Now n is equal to nt minus w, and effort is always equal to t. Is it clear? Now mechanical advantage formula is load upon effort. We substitute the values of load and effort. Load is equal to nt minus w and effort is equal to tension. We substitute here nt minus w upon t. What we get? N minus w upon t. This is equal to n minus w upon e, effort. Is it clear? Now what can you see here? Earlier when we were talking about the ideal machines, the mechanical advantage was equivalent to n. Isn't it? Number of police in the system. Mechanical advantage was equivalent to n. But it is coming n minus something. So the mechanical advantage has been reduced when we consider the weight of the pulley. Is it clear? The mechanical advantage is no more equivalent to the number of pulleys in the system. It has been reduced. Okay, it is n minus w upon e. But the motion of the string is not dependent upon the weight of the pulley. So velocity ratio remains the same. So velocity ratio is still equal to n. Now we find out the efficiency. We have a relationship between the mechanical advantage and the efficiency and velocity ratio. So efficiency is equal to ma upon Vr. We substitute the values of ma upon Vr, n minus w upon e upon n. On solving we get 1 minus w upon ne. This is the formula for the efficiency. Now you can see in this formula, again it is not equivalent to 1. 1 means 100% efficiency. Here also the efficiency has been less than the efficiency is less than 100%, and it will be equivalent to 1 only in the condition when we take w very small. If we take the pulleys merely of negligible mass, then only the efficiency will be close to 100%, or the number of pulleys is large and is very more number of pulleys. But if we take more number of pulleys, naturally the weight will also increase. So what we should consider? The weight of the pulley should be as light as possible to get an ideal efficiency or 100% efficiency. The other things for greater efficiency, the lower block should always be as light as possible, and the friction in the bearings of the pulley should be minimized by using proper lubricants. Okay, so that there is no friction. Okay, so this is all about block and tackle system. I hope the chapter is clear with all of you. Please watch the videos once or twice to understand the chapter and do all the exercises that are given at the back. I have emphasized what is important in the examination. See, this chapter is very important for the examination because you more often get questions from this chapter. Ask on levers and also ask in the block and tackle system. One complete question in section B is often asked in the examination. Okay.